Okay, so we're looking at Unit 2 test question 2 here. This was a strange one where they had a bunch of various kind of like math terms in terms of like limits and whatnot. And then they had over here a bunch of, different definitions. So what does a jump discontinuity look like and different things like that. So I just want to kind of go through down here, and I've drawn pictures of each of these. So let's start with the jump discontinuity. Jump looks like this, where the left-hand limit and the right-hand limit are not equal as I approach C. So the left-hand limit here is something like, I don't know, whatever this is, maybe like a 5, okay? And the right-hand limit is maybe over here, something like a 2, all right? So the left-hand limit and the right-hand limit are not equal. And so going back over to here, that is this guy here. Look, the left-hand limit, that's the little negative sign, is not equal to the right-hand limit, all right? What does a removable discontinuity look like? Well, graphically, removable is, where is it? Here it is. Removable discontinuity is basically I've got a left-hand limit and I've got a right-hand limit. Oh, and they actually look the same. They look to be both maybe like 3, okay? That's weird, but now what is the function defined at C? Well, I've got a hole there. So the function is not equal to 3 at C. That's what a removable discontinuity looks like. And if you look at its definition, it's this. Here you can see the left-hand limit is equal to the right-hand limit, yet the function is not equal to those. And so that would be known as a removable discontinuity. Okay. The next one is an infinite discontinuity. That's where's that one? That's here, where the left-hand limit is either infinite and or the right-hand limit is infinite. Okay, and that looks basically like this over here. Here's my letter C, my C value, my X value. So I've got some kind of limit as I approach C from the left. It appears to be infinite. Remember, the limits are the Y values. And maybe it'll be negative infinity. It doesn't have to look like this. You could have things that go up both like that, okay? So it would be an infinite discontinuity, okay? Let's see, what else do we have here? Continuous. This is the one where it's actually almost like this one, the removable discontinuity, but in this case, the function is defined at C and it is equal to the limits. And so if we look at it here, this is continuous. So here, look at this. My left-hand limit is whatever this is. Let's say it's 10. And my right-hand limit is 10. And the function is also defined at 10. And so that's what these three things say. Left-hand limit is 10, right-hand limit is 10, function is defined at 10. Okay, so that means it is actually continuous. These were all discontinuities. This is continuous. These now are talking about non-differentiable functions here. So let's talk about number 5. Number 5 is a corner. Where is it defined here? The one-sided derivatives are finite but differ, okay? So my corner is up here, meaning my one derivative, the limit of my derivative here is maybe like, I don't know, this derivative is finite. Let's say it's 3 for that slope. And this one happens to be negative 3 for this slope. And so as I approach C from the left, I appear to have a positive slope. As I approach C from the right, I appear to have a negative slope. And so therefore, what they're kind of saying is that the derivatives they're an actual value, but they're not equal. That's what they're saying here. They're finite values, but they are not equal. And from the left side and the right side. That is one way of defining a corner, okay? The cusp is the same idea. It's number 6, but instead of being finite, they're infinite, sort of. And so a cusp looks like that rather than being. And then finally, here's your vertical tangent line, and that's this one here. The slope of the secant lines approach infinity from either